Hi, this is Seth Fleishman with World History by a Jew. I told Dr. Josh and Megan I'd give them an assist with some of their Mesopotamian math. If you watched their earlier videos, they said that math wasn't really their thing, so math happens to be my thing. And I have my own lecture series. I told them I'd give them a hand. You can look up World History by a Jew on YouTube and you're going to find nothing. This is the first time I've ever done a YouTube video. I do all my lectures in person for charities, and normally I do, say, weekend events full of history, and I'll speak 2 or 3 times over the course of that weekend, but I'm never on film. So congratulations for seeing me on film for the first time. So let's jump right into Mesopotamian math. So what makes Mesopotamian math different than our current math is we use a 10-based system. In fact, most of the world uses a 10-based system, and archaeologists believe that it just goes back to us having 10 digits. So you count 10 on your fingers, and that's the easiest way to start off as your base with math. But in ancient Mesopotamia, they had a different system called 6-base. And 6-base is much better for when you're, we'll say our pre-computer days, for when we don't have everything written down, and even going back further than that. So why you need a 6-base is, instead of dealing with 100 as your core number, you have 60 as your core number. And the advantage of the number 60 is how many ways you can divide it. So when you look at 100, right, you know you can divide 1 into it, of course, every number. Then 2, okay, you get 50. You can divide into 4, you get 25. And you can divide into 5, okay, 20. But then it kind of falls apart after that. So you know of the first 6 numbers, you can divide evenly into it with 4 of those. Well, when you have a base 60, all 6 of the first numbers you can divide into. So 1 divided into 60, of course. Then you have 2 into 60, so 30. You have 3 into 60, so 20. 4 into 60 is 15. And 5 into 60 is 12. And 6 into 60 is 10 each. So what the advantage of that is, by being able to divide through 1 through 6, that's a huge advantage with fractions. And you're dealing with partial payments or partial amounts. To have that 6 base and have a solid number to represent the fraction is a tremendous advantage, which is what the Mesopotamians figured out at a very early stage. Now, they've left us a legacy, which I'll get to in just a second, but what I wanted to mention first is the Mesopotamians are not the only ones who noticed the advantage of the 6 base. Since Megan is from the UK, she'd appreciate that pre-1971, the British also used a modified 6-base system. Right, so we know, if you think about your Charles Dickens novels, or when you have your 240 pence equals your £1 sterling, and 12 pence equals a shilling, and 6 pence equals half a shilling, then this gives you this same base that the British used is what the Mesopotamians used. Now, I'm not saying the British system was based on the Mesopotamians, but it has the same logic behind it, the same reason for using it. And by the way, that old system that went away in 1971 did last about 1,200 years. So it was started being used somewhere in the probably late 700s. And like I said, it didn't go out until 1971. So let's talk about some other 6-base numbers in Mesopotamia. So all their weights and measures were based on this core this core 60 number. So let's look at a talent. And by the way, anyone who's read about Greek history or Roman history is familiar with a talent. Well, to the Mesopotamians, a talent was about 30 kilograms, but kilogram was not a measure they used. It's a measure we use. It's just fortunate that it's a pretty even number to remember. But what you may not realize is that 1 talent divided up into 6 mina, and 6 mina then divided up into 3,600 shekels. So here we have shekels, which is another familiar number to all of us, right? Because if you know anything about Israeli currency, it's in shekels. And this is the same idea. I won't get too much in the monetary system, but kesef, which means silver in Hebrew, also means money in Hebrew. So silver was their base system, and that tiny weight that you'd start with would be a shekel. So 3,600 shekels equals 60 mina, which equals 1 talent, all using that 6 and 60 number. And then you have the beringa. So the beringa was equivalent to a liter, approximately. And if you had 60 sila, you had a beringa. And if you had 3,600 gin, then you had a sila. So Again, 60, 60, 60. I'll tell you another little trick, and this is, as I said in the beginning, we think that everyone started with this 10 base just based on us having 10 digits. Well, there are some that argue that the Mesopotamians actually had a different way of counting. So instead of doing this 1, 2, 3, 4, instead they take one hand and they count each of the bones in their fingers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they could get to 12 using one hand, which would be a distinct advantage when you don't have anything to write down and you're counting with your fingers. So now let's look at some legacies to the system of the Mesopotamians, because we still have some leftovers in our society today. One is, let's look at an hour, right? That's probably the first thing everyone thought about. When you have 1 hour equals 60 minutes, which equals 60 seconds. We can thank the Mesopotamians for that. And let's look at geographic coordinates, right? Geographic coordinates also use this minute system. Again, thanks to them. And then let's look at circles, right? So circles, 360 degrees. 360 degrees is, again, has the 6 base, and we're dealing with the 60, and so 6 times 60 equals 360. And now let's look at the sky as a big circle. Now the sky, if you look at it in 360 degrees, you would notice how, as you're watching the sky every night, you'd see these celestial entities kind of crossing the sky. So the Mesopotamians divided the sky up, this 360 degrees, into 12 equal portions. And each of those 12 equal portions took around the cycle of a moon in order for them to pass. So that's where we get a month, right? So the month became the month. And they had a lunar calendar based on that. And then whatever the stars were aligned, whatever the alignment was when you were born, the Mesopotamians believed that this had an influence on your future. Now, you could always be influenced by what you see out in space, but the most impactful configuration of these celestial spheres would be the month that you were born. And so that was 1/12 of the sky. That was during one of the months or months. And then that, of course, leads to the zodiac. So when you talk about the zodiac system, this horoscopes and so on, that people still follow some in the newspaper today. I happen to think it's a little bit of a pseudoscience, but for those who do follow it today, you can thank the Mesopotamians. And if you want proof of that, then just go back to the Greeks, because the Greeks would call their astrologers by either the name Babylonians or Chaldeans. So again, this shows you the recognition even by the Greeks of this horoscope system that the Mesopotamians developed, specifically the Babylonians. And of course, it goes back to the 60 base that I started with. And so the next time you see a horoscope in the newspaper, or you see a coordinate on a map, or the next time you just look at your watch, you can thank the Mesopotamians and their math. Hi, this is Seth Fleishman with World History by a Jew. After my first Mesopotamian Math, Part 1, I'm now back for Mesopotamian Math, Part 2. Make sure you see the first part before you watch this. It was a video from November of 2018. Okay, so Mesopotamian Math, Part 2. Let's talk a little bit more practical about how they used math back in ancient Mesopotamia. So math for them was to solve real-world problems. So you didn't have these complicated exercises with chalkboards full of calculations. For them, math was about say, business transactions or accounting and this sort of thing. So why? Well, let's say if you've got land parceled up, so it's for calculating land parcels and making sure everyone has the amount they're supposed to. The length of a canal. So if you're building a canal, calculations related to that, like the number of man hours to build the canal. And then let's talk about farming, right? How many bushels of a given crop that's being produced. The amount of time, so whether you're building a canal or the crops or so forth, the amount of time you need to put into it,
or maybe just dealing with, say, missing quantities where you know part of the story but not the rest of the story, so you need to calculate the missing quantity. So these are all real-world problems, and this also leads to a very obvious difference between their math and ours is they didn't really use negatives so much because you don't need negatives in any of these applications. So let's talk about some more differences between the systems. So this is our system, which is the modern system, versus the Mesopotamian system. So writing Mesopotamian numbers, let's talk about the positional notation. So their positional notation was actually better than the Romans that came long after them, right, where you have the I's and the B's and the X's and so forth. They did use positional notation, which is closer to what we're used to, although it is a different type of notation. So we, of course, use a base 10. So by base 10, say we have 1 plus 10 plus 100 plus 1,000. So each of those steps in the position, if you add all those up, you get 1,111. Now let's talk about with a base 60 system. You have 1, next position 60, next position 3,600, next position is 3,600 times 60, which is 216,000. Total those up and you get 219,661. So you see there is a positional difference, but nonetheless you can tell by position at what level you're dealing with in the calculation. Now let's talk about kind of a weakness to their system. At least I'll call it a weakness in our minds. That is, they did not have a zero. And so they would either leave a gap, so especially in later times they left a gap to signify a zero or a nothingness. But in earlier times you may not even have that. So like 30, let's take the number 36 in cuneiform would be written the same as 306. Which would be written the same as 3006, and you just have to know what you're dealing with based on context. So this zero system that we use was not really fixed until the Arabs brought us the Indian system in 700 or so of the Common Era. And by the way, I should say that what made zero so popular in Europe, since I am the lecturer of world history by a Jew, I'll say that it was a rabbi. Rabbi Avraham ben Ezra's system. He wrote a book called Sefer HaMispar in 1146. Sefer HaMispar just means the book of number, and he really is what, with this book, made zero the way we use it today in practice throughout Europe. Let's move to another weakness. Again, this is weakness by my definition. Maybe someone from ancient Mesopotamia wouldn't call it a weakness, but let's talk about decimals, for example. Decimals can cause a similar confusion in their system. So they use kind of this, what we would call a floating point system. A mathematician would call it a floating point system. I don't know if the common man would call it that. But let's just say, similar to I was showing you how you had to know where the zero was, the decimal is the same way. So if you had zero, let's say you take 0.0036 would be written the same as 0.036. That would be written the same as 0.36, and that would be written the same as 3.6, or even to 36. So you really have to know, again, in context, where your decimal place would be. So, like, even, and keep going, 360 is the same as 3,600, which is the same as 36,000. So this is this floating point. You also would have to know the context. And by the way, anyone who knows how to tell time, this helps. So pretend you're looking at a clock face, and this makes a little bit more sense. But 5.5, we'll say, written in base 10 would be 5 and then space 30 in base 60. So remember, when I say 5 space 30, this 30 is really 30 over 60. So we have 5.5, which is 5 space 30. And if you want it more in a context, know that 30 is really divided by 60. So give me another example. Let's say 2.25. So 2.25 in base 10. Now we're going to convert to the base 60. That would be 2 space 15. And again, it's like 15 over 60. That's your 1/4. 7 3/4. So 7 and then space 45. So again, 7, and then it's like having 45 over 60. We're thinking like we're looking at a clock. So decimals could be a little bit confusing. You definitely have to know your context. Division was also very different for them, whereas Mesopotamians had a clear addition, and they had a clear subtraction, and they had a clear multiplication. They did not have this fourth category of division, at least the way we think about it. So there was no long division function. Instead, if they're dealing with division, they'd really use multiplication with a reciprocal. I don't want to get too complicated here, but let's say you've got 2 divided into 10. So what they would actually do is take that 2 and flip it around for the reciprocal. So the reciprocal of 2 is 1/2, right? It's 1 over 2. So 1 over 2, which is 1/2 times 10, equals 5. So by flipping around to use this reciprocal, you get the same thing, right? So 10 divided by 2 equals 5. Or if you take the reciprocal and say 10 times 1/2, you also equal 5. So it still works. It's just it's more like just a modification of multiplication instead of having a separate division category. Now, these reciprocals can get really complicated. I intentionally chose an easy one since I'm just filming a quick video on this. But there have been tons of tables found of reciprocals. So, the reciprocal of, and not only that, but just remember that it's always out of 60. So if you've got the reciprocal of 3 over, of the reciprocal of 3, right? So you and I would be thinking, oh, well, that's 0.333, but to them it's really 0.20 because it's over 60, right? So 4, if you got the reciprocal, you and I are thinking 0.25, but to them it's really 15 because it's 15 out of 60. This goes back to my first video where you really have to know the sexagesimal system. Reciprocals in practice were probably most commonly used for calculating interest, right? They did have interest like we have now, and you would need the reciprocals for doing these smaller percentages to figure out how much to add. Now, getting back to these tables, so we have these very complicated numbers, and we just found tables upon tables in cuneiform. So all these tablets, you just see like tables for reciprocals, tables for multiplication, tables for fractions, tables for square roots, tables for conversions, and much, much more. So basically, you had all these tablets that were cheat sheets. So we'll call them, you can't call them cheat sheets because they weren't sheets of paper. We'll call them tattle tablets. So just imagine you have all if you were a mathematician back then, you have all these tattle tablets to help you with the various calculations. Now, let's talk about how you use those tablets in practice. Now, obviously, if it just gives you the straight answer, well, that's easy. But let's say you're dealing with numbers in between. Like obviously 1/6 is easy. That'd be on your tablet. But what if you're dealing with 1/7? What if you're dealing with 1/11? What if you're dealing with 1/13? So if you take 1/7, this is like an infinite sexagesimal fraction. Like you're just not going to have the ending of what 1/7 is. So to the Mesopotamians, it was okay to use estimates. In fact, they would actually solve a problem if they realized that the decimal would go on forever. They would just solve the problem by saying, okay, here's the answer, and by the way, this is an approximation. Like literally, they'd have like the sentence, this is an approximation. So by doing this, they're kind of covering themselves. And if you think about it, they're not sending men to the moon. Maybe the ancient aliens people will tell you they were. I think that they were not. And if you're not sending men to the moon, then it's okay using estimates for, say, like a few acres of land or a few bushels. It's okay. You don't need to go round to the decimal to the nearest thousandth. Now, let's talk about the most famous decimal place, and that is pi, right? So I don't think you can have an estimate more famous than us when we calculate pi. The Mesopotamians, let's talk about pi, for example. Pi is simply the fixed ratio of a circumference of a circle to the diameter of that circle. So in other words, so you're going to take the diameter of the circle, and there's relationship to the circumference of the circle. And the Mesopotamians knew that it was about 3 to 1. It seems in earlier days they really did calculate it probably exactly 3 to 1. In later times it was more like 3 1/4, so 3.125 in our terms, which is not so bad compared to what we now calculate as 3.14 and blah blah blah. So 3.14 versus 3.125 for their calculations would be good. And how they would represent it, of course, they didn't use the Greek character pi, but to them it was basically a fraction of 25 over 8. So if you look at 25 over 8, that's going to get you your 3 1/4. Now and by the way, they knew the calculations, right? So a circumference of a circle would be what we call 2 pi r. They'd use the same formula. An area of a circle is pi r squared. They use the same type formula. Again, these are not scientific measurements. These are land parcels. So this was a workable estimation of reality for them. Now let's talk about in terms of calculating area. They were dealing with land parcels mostly when they're calculating this area. And land parcels were owned by the king. They were leased by the king. They were owned by the temple. You had systems of serfdom. You had businessmen. You had big landowners. You had plantations, to use modern terminology. So parceling out land for all these various different categories was very important. And determining the space was vital to their business model. And they calculate area just like we did, length times width, right? So if you had a rectangle 4 kilometers long and 3 kilometers wide, you would just multiply those to get 12 kilometers. And so they had a similar system. Now, they did have more complicated formulas. It's like, say you had a trapezoid. Well, they knew how to deal with the trapezoid. So if they're looking at a trapezoid, they would just say, they would take the average of the two different sides versus the one single side. So to give you calculations, let's say it's 6 cubits wide on one side, and it's 4 cubits on one side and 2 cubits on the other, and the side that's 6 cubits was the same on both. Then you take the average, so the 2 cubits times the 4 cubits, that average is 3 cubits. So 6 cubits times that average number, 3 cubits, gives you 18 cubits for the area. This would be very simple for them. Did this all the time. And by the way, they did even more complicated ones where you say you have to have a circle connected to a trapezoid. Again, they would know how to use the two different, use pi for getting the one portion, and then using this length times width calculation with averages to get the other. Very simple stuff for them. Now, let's talk about the Pythagorean Theorem, because they had to deal with triangles a lot too. So they were well versed in dealing with the calculations related to right angles. And this is where basically, first of all, I know you're all thinking Pythagorean, that was Greek. Well, so Pythagoras lived around 500-ish BCE. Now, we're talking about Babylonian tablets that go back 1,000, maybe even 1,500 years before he lived. So obviously, he was not the originator of the concept of dealing with the right angle. But in their terminology, the Mesopotamians were well versed of this a squared plus b squared equals c squared concept that we all learned in algebra. And so this knowledge was well over 1,000 years old when the Pythagoreans supposedly discovered it. So we knew that the Mesopotamians were well versed with dealing with right angles. They're well versed with dealing with pi, and then finally they also were well versed with algebra. So you can probably see from my previous example, we're getting closer to algebra. So they did have their own quadratic formula. The quadratic formula you should all remember from school is where you have the ax squared plus bx plus c equals 0. And then based on that, you get your quadratic formula for solving for x. And they had the quadratic formula. They did have their own square root method. In fact, they were very advanced in the square root calculation, so they could solve for this issue. And this would be like, when would you use this? This would be like, okay, well, I'm calculating a building where I know maybe it's like by a river or something. I'm calculating a building where I know one side needs to be 2 times the other. You would see this being used. If I'm dealing with profit models, like for a business enterprise, it helps to have algebra. If you're talking about the speed of different shipping boats down a river, helps to have algebra. So in conclusion, the Babylonians were excellent mathematicians, but in practical terms, they already were using math that the Greeks supposedly discovered 1,000 plus years later. and they knew how to use math in the most real terms that we can all still appreciate today.